For my final project, I'm working on a real-time adjustable LQR system. So LQR is great in that it can optimally solve linear quadratic regulators when your system is linear and any rewards you want are quadratic. But the drawback is that you need to have a perfect model of your system in order to get these optimal results. So in this case, we're actually collecting training data in real time and then using that to figure out a linear model of our system and then using that to create the controller. So there is some noise added into the system, and that's why you see the plane shaking. So the target of the plane is to be exactly in the center of the screen, and you can see that with the red line on the top. You can see how it sort of hovers around the center, and it uses that data from its hovering on the center in order to generate a system, in order to generate a model of how the plane works. And so this model is going to be a curve of the amount of force based off of the amount of thrust. So here on this bottom graph, you can see the x-axis would be the thrust output of the controller, and the y-axis is the amount of force put on the plane. And you can see that you actually do need to have a positive thrust output in order to have zero force on the plane. This is, of course, because gravity would be pushing the plane down. And the red line is the actual curve, and the green line is the LQR model's estimation of the curve. So in this case, it seems like it's actually doing a pretty good job of estimating the curve. It does sort of wobble around a bit, but it's sticking right around that x-axis to give a pretty accurate model, and we can see that our plane does a good job staying in the center. But this is of course an easy case because the actual curve is linear and it's using a linear model to approximate a linear curve. But I could switch that to a quadratic curve. Here the negative is just the negative version of the quadratic, but you can see that it does first a little bit struggle. You can see that its offset is actually negative for a bit, but then it does eventually end up with a model that is tangent to the quadratic line at the point that's trying to hover about, which works as a pretty good model for the purpose of the system because it's a linear approximation in the area that we're fitting. And we can also switch this to another nonlinear curve like a square root curve, and of course it does overshoot initially because it's applying more thrust because it was still using the previous curve, but as it collects more training data it ends up with a better model, and now our linear line is a tangent approximation for the square root curve around y equals 0. But of course these are all somewhat easier cases because they are all monotonically increasing. So as a more difficult case, we can give it a sine wave. So there's multiple places here that where we'd be increasing or decreasing depending on what value we're giving it. But so here it looks like that our model just sort of picks one point of the sine wave and just ends up just approximating around that point, which does work effectively in this case, and we see that our model can actually pretty well keep the plane in the position. However, in all of these cases, the sort of the point that we're trying to hover about is close to each other, so the model doesn't have to make any too drastic changes. Something we can do to be a little bit more diabolical to our model is to actually negate the thrust curve. So instead of needing a higher value to generate more upward thrust, we need a lower value to generate more upward thrust. So here when we negate the thrust curve, we can see our model immediately drops off, hits the floor actually, but now it's starting to recover as its learned model does approach the real model. And of course we can do the negated thrust curve for all of them, and it turns out just fine. Something we can do is also use the negated thrust curve on the sine wave model, and over time it looks like we're just going to approach a tangent line to that sine wave, and it works fine. But then when we now negate the sine wave model, our model just stuck on the floor, and in this case it sometimes will recover, sometimes won't recover from this, just because sines will just get stuck on the floor. We just can't collect any more data. In this case it looks like we are recovering, but it looks like we're hovering around a point that is no longer near the center of the graph, so we probably have some tangent line way out off the plot, and we can switch back to a linear model and watch it crash or negate it and just really punish it until it does come back. So in general, it seems like for small changes in the model, it works pretty well, like such as switching from a linear one to a quadratic one, or from a quadratic one to a square root one. But when we have more drastic changes in the model, sometimes the learning rate isn't high enough for it to actually catch up, and we will catastrophically crash into the floor or ceiling. Thank you for watching.